Okay, so with all this chirping about electricity and magnetism being the same thing, we need to discuss what happens to a proton or an electron when it experiences a magnetic field. So the force that that particle will experience is given by this particular equation. And I would like to draw your attention to this little symbol here. Do you notice that I just left Q bumping up against the V there, and it's implied that it's multiplication, but I went to the effort to specify that there was an X here in that multiplication? It's because this thing here is a cross product, which is a type of vector multiplication, which if you've taken calculus and vectors, you've talked about a little bit. Cross products takes a vector and multiplies it by another vector and returns a third vector that is perpendicular to both. So this force, based on this cross product inside of its equation, is perpendicular, therefore perpendicular to both V and B. I maybe buried the lead here. What is V? Well, V is the speed at which the particle is traveling. So the speed of the particle. And it's got a vector hat on it, so it matters what direction it's headed. So if it were going this way, we'd write it as an entirely horizontal velocity. B is the magnetic field. And Q is the charge. Now you notice I've written down here that the magnetic field is perpendicular to the screen. So I'm going to chop the screen up into two pieces here. A place where the magnetic field is 0 and a place where the magnetic field is, let's go with 3 Teslas, which is huge, but whatever. I don't want to bog this down with too much scientific notation. And it's perpendicular to the screen. So if this is X and this is Y, then in and out of the screen is Z. So that's going to be 0, 0, 1. Now we've got a 3-dimensional vector. If you have taken calculus and vectors, you know how to do cross products. So you could do the questions this way, and it's really slick as long as you understand the cross product algorithm. For the rest of us who haven't necessarily taken that class, we're just going to write this as 3 Teslas out from screen. Okay. So I'm going to take a charged particle and I'm going to let it enter this electric field. So it's going at some speed like this. Let's give it a speed of, I don't know, 400 meters per second, which is not fast for a proton or electron, but that will do. Okay, now it enters into this field area. So I'm going to be able to calculate a number for this shortly, but we've got to figure out which way it's pointed. So again, this all obeys the right-hand rule, and because the screen is going to flip on me, I can't guarantee that I've got this going in the right direction. But what we can talk about is what's perpendicular. So if you have a magnetic field that's coming out of this screen and you have a velocity going that way, the only thing that's perpendicular to this direction and that direction is this direction. And if you use your right-hand rule, well, I'm not even going to try. If my magnetic field is coming out of the screen and the particle is going this way, the force is going to be pointing in this direction. So that particle isn't going to be able to travel straight this way. It's going to start being accelerated that way. So it will start at some point to travel like this. But when it's doing that, if the magnetic field is perpendicular to the screen and the particle is now heading this way, the direction that is perpendicular to both of those is no longer straight down. You can see that. This isn't 90 degrees. The new perpendicular direction is like this, which is going to make the particle bend even more like this, which means the new 90 degrees is like this. And then the new 90, it's going to make it do this, and then the new 90 degrees is like this, and then it's going to make it do this, and the new 90 degrees is like that. And of course, the particle doesn't do this in chunks like that, right? It's not like, okay, I'm going to make 1, 2, 3, 4, 5 different course corrections in order to follow. It's going to do it continuously. So if I take this path and I make it continuous instead of blocky, I get something that looks like a semicircle. And this magnetic force at all times is pointing towards the center of that circle, which provides the centripetal force necessary in order to put this particle on a circular path. So now that I've got the diagram there, I can do a little bit of calculating. So let's say a proton enters this field, exclamation point. Okay, so the force acting on that proton will be its charge, which is 1.6 times 10 to the negative 19. Its velocity, which was 400. Its magnetic field intensity, which we set as 3 teslas. And because we have everything arranged so that it's perpendicular, right, the velocity is perpendicular to the magnetic field, then I can simplify the cross product just by multiplying these two numbers together and knowing that it points towards the center of the circle. So I'm going to pop that in there, towards center. Okay, so I'm going to get that force. Let's see, 1.6 times 10 to the negative 19 times 400 times 3 gives me 1.92 times 10 to the negative 16 newtons. Okay, lovely. Now, if that force is causing this thing to travel in a circle, then I should be able to work out some stuff about centripetal force. So I'm gonna pop that up here just so we can remember way back from Unit 1. Centripetal force was mass speed squared divided by the radius. So if this force went here, I know the mass of a proton is 1.6 times 10 to the negative 27 kilograms. That goes here. I know the thing is traveling with a tangential velocity of 400 meters per second. That goes here. The only thing left to calculate then is the radius of that path. So if I were to do that, take this force that I just calculated from the magnetic field interaction and I make it the driver of a centripetal force. My radius pops up here. The mass of the proton is 1.6 times 10 to the negative 27. The speed of that proton is 400 meters per second. And the force ends up in the denominator, 1.92 times 10 to the negative 16. So my radius, let's see what that ends up as. Put that in the denominator, times 1.6 times 10 to the negative 27 times 400 times 400 equals 3.83 times 10 to the negative 6. So the radius of that circle is 3.83 micrometers. Okay. If that's the radius, in order to get where it actually lands, I need 2 radii. So double that, I'd end up with 7.66. Let's switch colors. 7.66 times 10 to the negative 6 meters. Okay, lovely. So let's dissect this a little bit. That's pretty small, right? 7 micrometers. So if I wanted that to be a little bit bigger, how would I make that bigger? Well, to make this number bigger, this number would have to be smaller. In order for this number to be smaller, I'd have to either slow the thing down or reduce the magnetic field. And we did discuss that this was a pretty scary field. So what if I go through and I change this from 3 Teslas to 3 milliteslas? Or, yeah, let's go 3 milliteslas. That would be 3 times 10 to the negative 3. So that means there's a times 10 to the negative 3 in here, which means that this becomes 10 to the negative 19, which means this is 10 to the negative 19, which means this is 10 to the negative 3, which means this is 10 to the negative 3. So suddenly I have something showing up 7.66 millimeters away from its entry point. Well, that's about that far. So here's the neat thing. If I were to fire protons into this magnetic field at that velocity, they would have to arc around and they would have to land here. And that location was based on their mass right here. So what if I did the same thing with a helium? Well, if the helium got up to 400 meters per second, that number doesn't change. If it's introduced into this magnetic field, that number doesn't change. And if I take the force and pop it in here, these numbers are the same. This is the only one that changes, and the helium has 4 times the mass. So this radius would be 4 times the size, which means this gap would be 4 times the size. So you would have a machine that took protons, right, hydrogens, and heliums, and deposited them in 2 distinct locations. So if you could get a detector here and a detector somewhere else, you'd be able to pick up the presence of hydrogen in whatever garbage you were zipping down here at 400 meters per second. The heliums in this garbage would end up somewhere else. The carbons would end up somewhere else. The nitrogens would end up somewhere else. So if you take something that you don't know about, like hemoglobin, or a really complicated protein, right, something you find in the body, but you don't know the percentage of carbons, nitrogens, oxygens, etc., you take that molecule and you vaporize it with a high burst of like a high voltage electric field, right? You blast that thing apart. And then because it's in an electric field, all those little bitty bits go flying this way, right? They get accelerated up to high speeds, however fast you want them to go. Introduce that stream of charged particles into a magnetic field, and that magnetic field will tidally sort all your carbons into one pile, all of your nitrogens into another pile, all of your oxygens into another pile, and you can determine, based on the frequency of the detectors, not only the atoms that are present inside of that protein, but the proportion of atoms inside that protein relative to everything else. So if you were to do this to water, for example, you get 2 hits at the hydrogen spot for every 1 hit you get at the oxygen spot, which lets you deduce that the chemical formula for water would be H2O. So if you've ever sat through chemistry class and wondered, how on earth did they figure out that these molecules are made up of these little bitty bits that nobody can see, this is how. They built this machine. It's called a mass spectrometer, and it uses a magnetic field in order to steer those protons or carbon atoms or what have you into specific locations so that they can be detected, which is really kind of neat. So the problem set asks you to do a few calculations like this: determine a force, determine a radius, and then it asks you to think about how a mass spectrometer would work, using a pair of parallel plates in order to accelerate the particles to a particular speed, and then where those particles would land. So you're going to have to look back a little bit at the last video in order to get the speed of those particles, but the rest of it should be pretty straightforward. So I will leave you to it. Good luck.